Hey guys, welcome to another episode of Build Tensorflow, and today we're going to get rid of this vector thing, and we're going to introduce multi-dimensional arrays as a tensor internal representation for our tensor. This We're doing this because if you've used TensorFlow or PyTorch, you must know that tensors are of various shapes and sizes, and they can be reshaped into another to fit another shape. This is primarily because our data comes in various forms and formats, and generally you have a batch size, you have channels if you have an image, and you have the height and the width. So it's not only just a 1D vector. So we need our tensors to be able to support 4D arrays or 2D arrays, 3D arrays, stuff like that. So it's very useful to have our underlying representation with as an n-dimensional array. So to do that, what we'll do is we will make a new header file, say matrix.h. We will define our matrix class. And then we shall include, I like com.h, where all this is actually com.h, and even let's say operation comes from common.h. So after we've done this, what more do we need? Do we have like no loads? Yep. So let's just put all this in com.h. Alright, I think this is fine. Assert is actually CMath is actually only you need CMath for this file only, not the other files. So matrix.h. So what do we want here? So we want our matrix to support ND arrays. So the way TensorFlow and PyTorch do this is through two. It takes in two variables in its constructor. So let's say the first thing is a 1D array of it's called the val, and then you specify a shape. So let's say this is the shape, and let's template this thing so that it has support for multiple data types. And once we have this, let's get a constructor as public, because all the constructors are generally public. So okay, so you have this, and then let's say you have val public, and then you have int for shape. So your shape can be any n-dimensional, say like batch size, channels, number of channels, height and width. Or if it's an RNN, if you need it for an RNN, it will probably be batch size into you know the word embedding size. Here, so maybe it's 300 if you're talking about, maybe it's word 2x, so it'll be batch size into 300. That'll be batch size into sequence length into 300, which will specify n n data points of sentences. So this is what's up, and let's just assign variables this Have you guys ever listened to a song called Homecoming by Kanye West? I highly recommend it. It's pretty good. So we need some way to, so we have this, that's all we need essentially, and then let's do some assertions here, because we want our shape to be we want our shape to be something which can actually fit the number of the you know uh, number of data points in this vector. So that's a simple way we can do this check. Let's make it something private. Let's make a function that is private, and let's name it bool verify shape, let's call it. And then let's say the int is equal to p. No, let's not say int. Yeah, it should be int. And for so what we'll do is p into whatever the shape is, the shape at the particular dimension. So shapes are basically dimensions, right? And so p will essentially have the total number of elements that the vector should have. So we'll just check if var.size equal to p, return true. That means this is a valid construction of the matrix, or return false. That's a verifies shape. Verifies whether matrix constructed is valid or not. Alright, so let's add this. Let's add an assert here. So verify shape, and if this does not succeed, shape and number elements do not match of matrix. Alright, that looks good. So once we have this constructor, now we should define our operations, right? So it'll be something very similar to what we've already done before. So let's start with the common ones. Those will be simple ones. So as our output, it will be a matrix, and the input will be, let's define it for the addition. So const, let's not say const, whatever, we're not going to change it. So const matrix t, const matrix t, val, right? It says and so what we're going to do is we're going to assert that the shapes are equal, right? So we'll do shapes equal, and shapes of two matrices do not match this operation. So our shapes equal is another thing, and we should give val.shape as our input to this. This makes sense. Const shape2, let's say const vector int. So whenever you're passing a variable into a function parameter, and if you don't intend to change that parameter, you should send it as const and add. So const is an added check that this can't be changed. So once we've done with this, if shape dot size is not equal to shape dot size, return false without iterating it. For int I equals 0, I less than shape dot size I plus plus. If shape I not equal to shape to I turn false, and if everything clears, turn true. That means the shapes are equal. Shapes for plus checks equality of shapes for element wise operations. So once we have this check here, we can continue on and do something with it. So what we do is, yes, so what we'll do is very simple. Return matrix t. This would be, let's say, okay, so this is RHS. Let's call it RHS because we already have val here, so not to confuse things, val plus RHS dot val, and then we'll just send shape. So this should work, right? So does this overload? We have actually overloaded the vector addition with this, and it actually has an assert here as well, so this should actually work. Yep, this should be good, right? And let's do the same thing for multiplication and division, shall we? We'll be coming to the dot product, which is one of the main things here, our matrix multiplication between two matrices, and that will be challenging. I'd say we'll have to, in an ND array scenario, we have to be really clear of what kind of functionality we want to offer, because in an ND array scenario there's a lot of different ways or paths we can take. We can take the NumPy route and build in broadcasting support, and then we can match all the dimensions and then squeeze or unsqueeze the dimensions according to what the other operands is in the operation. So we don't want to do that actually, because our use case is very small. Our use case basically has the need for ND array, element wise addition, subtraction, and generally we want it in the case of matrix multiplication, we want an ND array which multiplies a 2D matrix. That's it, a 2D matrix, because all of our weights, we are basically targeting the multi-layer perceptron, a fully connected network, so the weights in those are just 2D matrices. So we're not thinking much about it, and if you think more about it, actually in convolution neural networks, the filters are the weights, so filters are a 2D matrix as well, and so it's essentially just 2D matrices. Even in LSTMs, if you think about it, the weights are just 2D matrices. they're never 3D or 1D. So that's all we need. We need a dot product operator which we can where our first operand can be any n dimensional array, and the second operand will have to be a 2D matrix, so a 2D array. So let's just check this out. What we've done is such, so that we know that we're on the right track, and then let's move on to the matrix multiplication. Matrix multiplication. Okay, let's go as main, and then let's create a int matrix. Let's say this will be 1 2 1 sorry 2. So let's include about that. Is everyone happy now? Yep. No, this does not work. Assert verify shape and number elements do not match. How do they do not match? It's actually 2 elements, and these are 2 elements. How do they not match? 2 1 2. So let's try to debug this. Okay, we haven't actually gotten our debugger out. Let's say our makefile is actually .g, so we're good. So let's just switch on the debugger. Get this on. What is this? I guess it's build / main.o. How about this? Cancel. Okay, something is definitely wrong. Main.o is definitely there. Okay, let's not bother about this right now. Let's just try to debug it without the debugger. So we have a matrix class, right? So that's value, and this is the shape, right? So why is it not checking out? Verify shape and number elements do not match. So alright. So we'll have to actually give. Alright, oh my bad. So we actually need this shape, and then we need a val here, and this would be t, and this would be l. So yeah, now it should run. Yep, it ran. So let's just check it out first. We should have some kind of print statement as well, but let's just say m2 and 1 2 1 2 auto m3 and 1 plus m3. I love the auto keyword. It makes life so much simpler. Yep. Now it should work. Nope. Use of m3 before reduction. Oh sorry, it should be m2. Yep, it ran. So if we want to get this working, so what needs to happen are 2 things. We need to overload the cout operator, the one after the cout. To do this, we need to create a friend class. We can actually, for some reason, define this here. So what we do is, yeah, let me just, so there's something called O stream, which is our basically our cout uh, operator, and then we're overloading this O stream, and we send this here, and then our matrix, in this case E, and M, and let's say template type name E, and then let's say okay, so let's just copy this again, template E, and then remove this front keyboard. Now what we do is just very simple, out M dot, well, that's it, and then we return out. Nothing to see here. That's it. That's all we do. Okay. Does this work? Okay, it does not, because we haven't actually overloaded our array thing. So to do that, so let's just not overload it. Let's just for in type 0 and then yep, 2 4. This is all we want, and 1 2 plus 1 2 is indeed 2 4. Let's do, let's say it should be 1 4. Yes, and then let's convert it to a float to get the result. It should be 1 1 actually. 1 1. Yep. So everything works fine. Now we want something like a dot product, which actually computes our matrix multiplication here. So to do that, we need to change our matrix class, and that will be a simple overload matrix D dot const matrix D and %RHS. Alright, so first we need to assert, we need to build our assertions for the matrix check. So assert dot product assertion. Let's name this dot product assertion, and then assert that the shapes are valid for matrix multiplication. Assertion shapes invalid for matrix multiplication. Once that's done, we can move on to our actual matrix multiplication. So let's do this and shape to matrix. Actually, shape 2 is fine. We should actually send our RHS dot shape dot product assertion. All right, so shape 1, which is the current shape of this matrix object, is the current matrix object is actually can be anything, but the last two dimensions should be equal. Should match with the dot product scenario, which is like the row can be equal, but the row of this matrix object has to be the column of this matrix object has to be equal to the row of this matrix object, the one on the right hand side. So that's essentially what we have to check. So what we do here is very simple, is shape shape so if shape dot size greater than equal to 2 is then 2, or shape 2 dot size is less than 2, return false. So we only support 2D matrix multiplication. So now that's out of the way, we can move on to for. So int row 1 equal to shape let's say shape size -1 -2 actually, and then shape 2 size -2, and this will be 1 column 1. So column 2 should be shape 2. If column 1 is not equal to row 2, return false, and then we return true if it is. That's about it, right? That's a dot product assertion. We return false if the size is less than 2. If any of the size is less than 2, we're going to ask for these values, and then not equal to 2. So shape 2 has to be a 2D matrix. There's no other way. So it's not equal to 2, and return false. That's it. Yeah, that's pretty good, right? Okay, now what we do is okay, once our dot product assertion succeeds, let's just return this for now to check our assertion. So this should work, right? Dot product constant and shape 2. ISO. Okay, we have some error here. Okay, I think we forgot to send a bool in. Let's make this again. Okay, this works. And then what if we have so this should be an assertion, yep, and then let's say that is an assertion, so we're on the right track. So what about this? This should not be an error. Yep, this is fine. Now we actually have to do the matrix multiplication. What we essentially have to do is to get inside. So for example, if we have this matrix, so we have to go in here go in here, go in here, go in here, go in here, until we have this matrix for all of these other dimensions. Once we have this matrix, we multiply it with this, we get the answer, we put it here, and then we go on till the next dimension. So in this case it is 1, but if this was actually 2, so then we would have need to go into the second dimension, second 2D matrix of 1 and 2, and then that would be multiplied by this, and then the value would be put in the second position of this dimension. So I hope this is clear, but it'll get clearer when we actually code this out. So let's get to it then. So what we need to do here is we need to find the exact position where we are at in a traversal of a matrix. So let's do that. Let's name this matmul, right? And then what we'll have is we will have our const matrix T RHS and RHS. Then we will have our vector of T ampersand our result, and then we will have we will need to have something that is a stack. So let's just use a stack of int here, stack index stack, let's name it, and then we will need to know what dimension we are in dimension. So once we have this, and then I think we'll have to include stack. This is an std primitive, and let's just name this a const. We need using namespace std after this. Once we have this, so now if our dimension, if our index stack dot size plus 2 equal to RHS dot shape dot size, let's say. That means we are in the state where both RHS and LHS matrices are 2D matrix format, or in 2D matrix format, right? Then we can form the matrix multiplication. If not, then let's say for int I equals 0, I less than shape dim I plus plus index stack dot push, let's say I index stack dot call, and then we call this function matmul recursively, so that will be RHS and then res and then index stack and then dim plus 1, because we go ahead once. Alright, this should be fine. So once we are in this 2D index format, we need to find position in LHS array where we are at. So to do that, let's say int p equal to 0 for int I equal to 0, I less than mm, uh, um, this should actually be uh, let's just make this a vector so we can actually iterate over it, and then this will be a pop back, and we can remove a stack from our comments because we actually need to see what the values in the stack are and not pop them. So what happens is index stack I into the number of elements that I've already seen, which would be elms I. What is elms, you might ask? Elms should be num L is seen num lm seen. So num lm seen would be let's make something called compute shapes for int I equal to shape dot size minus 1 I taking into 0 I minus then it will be int p equal to 1. Num lm dot pushback. Alright, so B okay, let's just say vector int elements shape dot size, and then we just return our elements. Num elements dot resize, let's say shapes dot size. How about that? Yeah, is push p and then p multiply equal to shapes I. How about that? This is good, right? So we will just put this every time the constructor gets called, to compute this. Alright, so we've done that. So now we can actually access this in our multiplication. Norm nmc into I, and then our value of p would be the starting point, and then we can actually do a dot product. That will probably be that will just be something like, I guess, dot, let's name something dot, and then let's name a dot product. Alright, and then we'll have our, obviously, our const RHS, and then we'll have our p, and then we'll have, what else will we have? We won't have much, so we'll have just RHS, and then we'll have start, and we should have our okay, right, so we should also have our resultant vector p res start, so this denotes, p denotes our starting point of in the RSH matrix for our multiplication, and res start would be the starting point of our right. Res start should actually be equal to RHS start, isn't it? Because up to now, no. So, oh, that's a problem. So we need to send vector int and res elements, so similar to num element seen. We need to send in res elements because that will be different, because our last two dimensions are different. So we'll give res start plus equal to index stack I into res elements I, and then res start equal to 0 dot product. So we've got our RHS, we got our res, and then int RHS start, int res start, and then we form our normal matrix multiplication. Looks good, eh? I think it looks good. So let's do the same thing here, where we go in row 1 equal to the shape shape. Let's just copy this, man. I want to do this same thing again. So we've got this, just a simple sanity check that our column 1 is equal to row 2 multiplication invalid matrices. Alright, once you've asserted this, so then it's pretty simple, which will be print, I equal 0, this will be an n cube thing, and this will be row 1, so we actually go for row 1, then int j equal to 0, let's say int k equal to 0, k less than equal to k plus plus, and then do sum to 0 for int j equal to 0, j less than column 1, j plus plus. This is our just a metric multiplication, and then let's just say where start, let's say sum plus equal to val, let's say RHS start plus I into column 1 plus j into RHS this should actually be LHS star. Yeah, this should make more sense. Alright, so LHS start was so RHS dot val, that would be just our j into column 2 plus k, and then this would be finally our resultant would be res start plus I into column 1 column 2 plus k into sum. Yeah, that should do it, and that's a dot product, that's a matrix multiplication. This should be fine, don't you think? One problem is that we need to define our res index stack, so let's do that. So let's write this. So okay, so we have a vector of t of res val, which would be res shape dot size for the zeros, and res shape dot size would be vector int res shape for int I equal to 0, I less than shape dot size minus 1 I plus plus, and then res shape dot push back the shape I, and then our final shape dot push back would be the column 2, called the column of the RHS dot shape shape so R is shape 0 1 1. Alright, so then we finally do matman to send in our RHS resval, and then our index tag would be vector int index tag index tag and then we would have our 0 dimension, start with the 0 dimension, and this should work fine. Return matrix t res var and then res shape. That should do it. This is our column dimension. You want to see if this works? Let's check it out. So what should be the answer, guys? The answer should be 5. There's an error. There's a lot of errors. Okay, let's go with the first one. Shapes was not declared in this scope. 39 of matrix. Okay. 39. Reshape shapes, compute shapes. Okay, shapes. Oh, alright. Okay, shape 2 was not declared in this scope. 69. 69. Shape 2. Okay. That would be shape. Yep. This, my man. And the third one is expected. This 91. 91 is 5 plus for this, and then the other thing is 48. No matching function call. 48. 142. Okay. 142. There is no matching function call to this. So is there not? Matman is fine. We are sending our RHS and then we sending our vector t. Oh, we got to calculate results. Alright. Okay. Alright. So we need to do another thing here. This will be auto res elements equal to compute shapes, and this will be a res shape, and we need to send this to, because we're missing this, we need to change the compute shape function such that we give back a vector of int let me see. Sorry. Compute shapes would be alright, now this is fine. There's another error, 100. Okay, 100 is where exactly? 100 is here. There's some error now. Alright, so matmal this index tag, we need to send res elements to. Yeah, now it should be fine. There's some more errors. No matching function call for res shape. Oh, alright. Res shape. Shape. Compute shapes is shape. Alright. One more error. Just one. Let's do it, guys. 71. Okay. So shape 2. Do we not have shape 2? Alright. Yes, we don't. Alright. Segmentation fault. Okay, I think we're going into stack process shape process -2 is equal to shape dot size. Alright, shape dot size -2. So RHS is actually LHS. We're always forgetting that. Got that, guys. I'm sorry. Actually, it is RHS. Damn. So we are sending in RHS. Yeah. Okay. This is definitely not in. So this dot shape dot size. Index tag dot size. Where do you think is the error, guys? We should really debug this, I think. Let's try to find something. This dimensions, and then we just doing this, then we pop back. Okay, where did the segmentation fault occur? Maybe we're doing this wrong, you know. Shape dot size, horizontal to shape dot size -2, -1, column 1, so column 1 and row 2, and then row 1, column 2. I'm stumped. What is happening here that's wrong? start. Define anything out of the ordinary, guys. You can't talk, right? Let me just try to figure this out. Let me just pause. Hey guys, sorry. So I found out the error. So the main error was in here, a matrix dot function. So when we are creating the size, we should actually get our size, what it is, and then the total size of matrix we have to initialize res val with that. So, and the second thing is the second thing was in our matmul. We had not added an ampersand here in the index tag, so it was going from scratch, and then we had a size -2 here for some reason, but I corrected that, and those were the only things that had a problem. Finally, I think that was it. um, and then you have this answer 5, which is right. So yeah guys, so we've actually made our ND matrix. So one cool thing that we can actually visualize this ND matrix, how it looks. So let's build something similar to the dot function, which would be like maybe a print function. So if you want to print our matrix, so we don't need any assertions here, and we need shape.size um, and then what we can do here is there's one more thing that we're missing here, which is matmul. Sorry, our matmul is done. Yeah, that's what we were missing here. So yeah, so if you want to build a print functionality, we copy this, rename this print, and then let's remove our res like this. We need to keep our index tag here, and then we can remove the rest elements also. If we are at and then we can do something like val, let's just start something like this, and then we can write out and then we can do this. And then something like that. I think it should be -1, and then we obviously have this, and for actually it should be shape.size, and then we can add this. So this should work. Alright, so instead of this we can just say return m dot print out, stack, and then 0 dimension, and then let's say vector int is our stack, right? And then let's try to just print this out. Okay, there's an error here. 1.1. Okay. I was not displayed in the scope. Is it right now? Right. Return out. Alright. So res was not declared in the scope. Alright, so obviously index tag. So we have our out here, stack, and then there's just dimensions plus 1, and then RHS was not declared. So where is RHS anyway? mm, 184. Hmm. 184. Okay, where did this error come from? 184 column dim. RHS was not declared in the scope. Oh, okay. Alright, so this is another function that we copied before. We forgot to delete it. Okay. Okay. Maybe we can copy this. I've already written such a function. Let's just copy this. Make life easier, and then we'll step through it. Right. Okay, let's see if this works even. Right. Elements, okay, elements was not declared. Elements is actually something I renamed by mistake. Num. Let's see. Right. Yep, 5, 1 by 1. So we've gotten this out. So what was our previous thing then? This is fine, this is fine, this is fine. Alright, so we're finally getting up to the 2 dimensions, to the last dimension, and when we get to the last dimension, let's see if this works. Curious about this. And P stack size. Yeah, this works, but we don't want 3 columns. We just want 1 column. So right. Alright, so we've made a printing function, and let's test this out with a big value. Let's say 1 2 4 5 6 7. So let's say this is a 2 into 3, or like let's say 3 into 2, and then let's copy the same thing here. We should get a 3 by 3 matrix now if we change this to 2 into 3. So our shape should be 3 by 3, so there should be 9 elements. Okay, 3 6 1 2 3 4 5 6. Verify shape number elements do not match of matrix. How do they do not match? 5 6, they do match. Let's look here what the problem is. Verify shape. So okay, alright. Oh, I'm sorry. So val.size should be equal to p. Okay. Does this work? Yeah, this works. I think there's a problem with the computing shapes. Shape and number of elements do not match. Let's put our good old debugger to use now. And then let's check this out. 1 second. So res val is 11 14 and 18. That's only 3 elements, and this should be 0 and 1. Res shape minus 1 3. So there should be 3. I equal to 0, I is less than shape dot size, which is 2 minus 1 1, is less than 1. Size into shape I is dot shape, push back is 3, and RHS shape. Shape. I is 0 3. The shape is 3. Shape is 1. Is 3 3 3 3. The shape could be values. Shape 3 3, and unless it suddenly changes for some reason. Okay. All right. Size into That's the problem here. Yeah, that's it. That's the right answer. Okay, thank you guys. So we did our ND array creation, and the next episode we're going to merge this matrix class into our tensor class. So all the data types of the value and the grad data types will be replaced by matrices, and you will give the shape for each thing. The shape for the gradient will be exactly the same as the shape of the vector of the val. So yeah guys, I hope you enjoyed this lecture. We created n-dimensional arrays, so that's one more step we've done towards creating our multi-layer perceptron network in this really small and lightweight deep learning framework. um, yeah, next time I promise you that we will definitely do GPU computing. And then if you actually want to see something that I've been working on for you guys especially, is our CUDA code. So I run it through GPU test. So as you can see, just look at what comes. Just look at this part. um, Speed of GPU multiplication is 83 microseconds. Alright, pretty good, I guess. And what's the speed of our CPU vector multiplication? I wonder. So this is the code I've been doing. It is 14,422, which gives us a speed up of almost 170 180 times the speed of the CPU. So that's what guys I've been working on. As you can see, the result is the same from the GPU and the CPU. This is what I've been working on, and in the next episode definitely we're going to finally dig into our CUDA code and try to get our matrix multiplication working on the GPU also. We actually have it working. I've done it. I'm just going to show it to you how to do it. And we did a lot today. We did the matrix class. We officially now have the functionality to get tensors of multiple shapes. So like it's kind of looking similar to the PyTorch or TensorFlow API. Yeah, so I hope you guys are still interested, and just tell me if there's anything you'd like me to do, or anything different you would like, or so, some problem you're facing with the way I teach, which is mostly coding. You just keep looking at the code and watch me fiddle around, which is not, I guess, very interesting, but I'm really open to suggestions. Alright, I'll end this episode now as it's getting really long. I think it might be the longest episode yet. Alright, have a nice day guys. Goodbye.